Hey, welcome back. Here we are. The videos that come after this one are all videos that have been previously published. So some of the, instructions that might tell you specific things about homework and assignments, you can just ignore those. These are just, this is my last of the new ones, dealing with the applications of the Radian measures that we were just talking about. So it doesn't do us much good if everything is all theoretical. So there are things that can actually be done with these things. So let's jump right into basically some word problems that would deal with radian measure and a couple of formulas. Okay, when you were in geometry, we had a formula for arc length. The arc length formula, actually, when we have radians, is a little bit simpler. It is simply the radius times the angle measure in radians, theta in radians. If you don't have the angle measure in radians, then you can't use this formula. So this is where we need to be able to go back and forth. So arc length, what's the arc length? The arc length would be like if you took a tape measure and you measured from here all around the curve until you get to here. So our arc length equals our radius times this angle measured in radians. It will work if it's measured in terms of pi, but also if you're just given a number of radians to go by. So let's take a look at a couple of sample problems. Okay, so we have a circle that might have a radius of 18.2 centimeters. Okay, 18.2 centimeters, and you want to find the length of the intercepted arc. Okay, so this could be useful if you had any kind of a circular thing and you needed to maybe wrap a piece of a cord around part of it, or part of a flower bed and you had the measurements and you needed to know how much fencing to go around. But there are some things that this could be used for. So if you are given the measure of the angle in radians, you can just simply use that basic formula that we just used, S equals R times theta. If it's in degrees first, you have to do a little conversion first. So let's take a look at these things. We'll look at this one first. So S equals R theta. So you'd simply need to put 18.2, your radius, times 3 pi over 8, which is already in radians, and put that directly into the calculator. 18.2 times 3 times pi divided by 8. Here's what it would look like on your Texas Instruments screen. You would put those things in. No need for parentheses or anything like that, because order of operations would do multiplication before the division that's at the end there. So that works out just fine. So 21.44 centimeters would be your arc length along the circle that way. Now, if you have 144 degrees, first you need to convert it to radians. And if you remember, that means multiply it times pi over 180. So we can do that. You can do that either by hand, recognizing recognizing that there is a common factor in there, or you could do this in terms of any other way that you wanted to. You could, reducing your fraction on the TI-83 plus was pretty easy. Don't forget your math frac button. So you'd do 144 divided by 180 and reduce. But whatever you can do in order to reduce that fraction, 4/5 pi, or you could even do the decimal equivalent would be fine. So 18.2 times 4 pi over 5. If you were to use your TI-83 plus calculator, that's what that would look like. 18.2 times 4 times pi over 5, and it would give you that answer. Now, if you wanted to, you could put in Since you've got the calculator anyway, 18.2 times 144 times pi divided by 180 will give you the same answer. So there's not really a need to have to reduce that. It will still work, especially if you're doing it as calculator work anyway. And for this one, you probably would be. So we would have that happening. So we have about 45.74 as our final answer to that problem. Okay, so moving right along, let's look at some more on the application type of side of this. For example, you can figure out distance between two cities, okay? This is an interesting type of a thing, can be used in positioning and maps and those type of things, because remember our Earth does approximate a sphere. So we can, if you know the distance from the center of the Earth to the edge, then you can use this as a way of figuring out distance between two cities as long as they're on the same longitude line, okay? Remember, our latitude is how many degrees it is if you're considering the equator as being 0. So this would be 26 degrees north latitude, if you remember from that section in your geometry class. If you don't, let's just kind of remember that. The latitude lines are the ones that go around the Earth this way. And so those lines are measured as far as the number of degrees tilted up from the equator. Okay, so you have Exampleville is at 26 degrees latitude because that's just so we can have some kind of an example. But let's take a look at Reno, Nevada and Los Angeles, California. Now they're on the same longitude lines. The longitude lines are the ones that go up and down. And if you say longitude, your mouth kind of goes up and down, and latitude, your mouth kind of goes sideways. So it's kind of an interesting thing with that. So if you know that the radius of the Earth is 6,400 kilometers, and I'm just giving you that little tidbit of information, and you want to find the north-south distance between Reno and Los Angeles. Well, what we do is we look at them and you think of them in terms of where they lie on the circle. So 34 degrees is where Los Angeles is. Reno is at 40 degrees. So if we were considering them as being on the same line like that, north-south, we would have it in this way. So in order to figure out how much distance is between them, in other words, we're looking for the arc length, we could take that 40 degrees minus the 34 degrees and find a theta of 6 degrees, and then use our arc length formula using 6,400 as the radius. So let's think about that. Okay, so I said theta was 6 degrees. Hopefully you understand that because 40 minus 34 is 6. Our radius, we said, was 6,400 kilometers. And our theta then needs to be turned into radians before you can use our formula. So don't forget, that means that you need to multiply it times pi over 180. So if we reduce that, since 6 goes into 180 30 times, that's pi over 30 radians. And we can use our formula S, which would be this distance from Reno to LA in the north-south direction, would be R times theta. So our radius, 6,400 times pi over 30. And you could put that directly into a calculator and get about 670 kilometers, 6,400 times pi divided by 30. Now, knowing that is one thing that you could do, would be to find a distance between two cities using that information. So there is one application. Another one would be if you had something that has to be wrapped around a circular object. Okay, we say a drum, but this could be any kind of thing where you have any kind of chain or rope that's wrapped around a circular object. So here we have a drum and you've got this rope that's kind of like twisted around, and they want to find out how much has to be from here to here if it's to touch that piece of it. Now you might use that as if it's part of a mechanism, okay, so that you know how far it has to be able to turn or something along those lines. Uh, I would imagine clockmakers would have had to have thought about things like that when they were winding, if there was any kind of winding spring inside of their clocks. But anyway, we have 39.72 degrees. It's in degrees, so we are going to have to change that over to radians. We're saying that we have a 0.8725 foot radius, so less than a foot, and we want to find our arc length. So if we multiply times pi over 180, since we're in decimals, we would just go ahead and take 39.72 times pi, divide by 180, and we get about 0.6932. So this is how many radians. Notice the degree mark is not there. So the theta being 0.6932 radians, so a little bit less than the radius of the circle in terms of radians, if we're thinking back to our definition of radians. So 0.6932 would be our theta, r would be our 0.8725, and you'd simply multiply them together, and we get 0.6048 feet. Okay, so about 6/10 of a foot. Okay, well, that's all well and good for that. Another application would be in gears. Gears are very interesting because this little gear, if it's going to drive the big gear, the little gear would spin around more times and it would move the big gear to where it needed to be. And as it's moving, okay, that arc length of how far it moves transfers over to the same arc length here, but it would turn into less of a turn. Okay, so let's think if the smaller one rotates 225 degrees, we want to figure out how many degrees the bigger one would have rotated through. So let's think this through. Our formulas deal in radians, so we'll just make sure that we convert that first. Okay, we'll convert it and we get 5 pi over 4. If we divided 225 by 180, we would get 5 fourths, or 1.25 pi would work also perfectly well for this. S 2.5, which is our radius, times our theta in terms of pi or in radians. And you multiply that out on a calculator, 2.5 times 5 times pi divided by 4, get you 9.8175 centimeters. So that's how far along this circle that turned. But remember that is turning into pushing this. If this is going this way, it's going to push this one 9.8175 centimeters this way. Now that's not going to be through as many degrees, and let's figure out how many degrees. Our S in this case is going to be the same. We don't have to figure out how much surface was touched, okay, because it turned this one 9.8 centimeters, so this has to also turn 9.8 centimeters along the edge. So we're going to use that same formula, S equals R times theta, but in this case, we're finding out how much theta equals. Little simple algebra, 9.8175 divided by 4.8. But it asks how many degrees. This answers in radians, so you have to do that conversion, 180 over pi. And this one, there's no pi's to cancel out, so you'd have to do 2.0453 times 180 divided by pi in your calculator, and you should get 117 degrees. You should go ahead and try that and make sure that it worked out. But we can see there that even though this one, the smaller one, turned through 225 degrees, the bigger one only turned through 117 degrees. It didn't turn as far. And that's what happens and the math behind what happens in gears that you may have observed physically in some of your dealings with life. Hopefully you have. We also have an area of a sector, if you remember from geometry. Once again, this formula is a little bit simpler once you're putting radians into the picture, 1/2 r squared theta. Area, radius, and theta in radians, or it doesn't work. And a sector of a circle is simply the pie shape. Okay, so in other words, the area of this slice of pizza. So we have 15 degrees and 121 meters, so it's not really a pizza if it's 121 meters. It might be a section or a sector of, in this case it says a field would be in that shape. You could have a field, so you need grass seed for it. You could have a place where you're trying to pave with concrete, where it's that sector, that piece, and you need to find out what the area is. So we would take r squared, the 121, and our theta, 15 degrees up here, would need to be turned into radians, so times pi over 180. 180 divided by 15 is 12, so that's where we get the pi over 12. So 1/2 121 squared times pi over 12. You would multiply that out, 0.5 being 1/2 times 121 squared times pi divided by 12, 1916.5 square meters. That would be the area of the field, and that could be used for whatever reason you needed to know the area of the field. And that's about it. I wish blessings upon you and encouragement. Jesus, please take care of each one of the people that are listening to this right now. I pray, Lord, for blessings on their life and understanding. I pray for a good day for them. Pray in Jesus' name. Amen. Have a blessed day.